Okay, let's talk about the first law of thermodynamics. So remember we said that we can think of variables in thermodynamics as state variables and transfer variables, and heat and work were describing the transfer of energy in and out of a system, so they were called transfer variables. And when you add energy to a system or subtract energy from the system, you're changing the total internal energy of the system. That is the energy associated with the motions of its molecules, atoms and molecules. So the first law of thermodynamics states that the change in the internal energy of the system can be achieved either by adding heat to the system or doing work on the system. So this W is work done on the system, and Q is heat added to the system. This is a very fundamental result of thermodynamics, and it has many applications. So we're going to see a few examples of this. To start with, let's talk about an isolated system. So if a system is isolated, that means it has thermally insulating walls. There is no thermal contact with its environment or with any other system. That means heat exchange is not allowed. Q is equal to 0. And if that's the case, the only way to change the internal energy of the system will be by doing work on the system. Another important example is the cyclic process. Cyclic process means we start with the same set of state variables and we end up with the same set of state variables. So P final is equal to P initial, V final is equal to V initial, T final is equal to T initial, and therefore we have internal energy final is equal to internal energy initial. So we reach the same state. Initial state is the same as the final state. And therefore, the first law of thermodynamics suggests the change in internal energy is 0. That means in this process, the heat added to the system is equal to minus the work done on the system. So we can summarize this result. Delta E internal is 0, Q is equal to minus W for a cyclic process. Cyclic process. And for the isolated system, we have Q is equal to 0. The change in internal energy is equal to W. Now this isolated system process is actually known as adiabatic process. So let's summarize the different ways of we can have these processes. So the adiabatic, what we call adiabatic process, is the one where we have thermally insulating walls. Q is equal to 0. It's the isolated system. That implies thermally insulating walls, and because of that, the change in internal energy of the system is equal to W, work done on the system. Another possibility is isobaric process. Now in this process, we have pressure is a constant. So if I calculate the work done on the system, work is minus integral P dV. If pressure is a constant, it comes out of the integral minus P integral dV from V initial to V final. So the work done will be equal to minus P V final minus V initial. So that's what I can say about the isobaric process. That's for the adiabatic process. And now I have isovolumetric process. In the isovolumetric process, the volume is a constant. And if you look at the work done, minus P dV, since the volume is a constant, it is 0. Therefore, the total work done is 0. So that means the change in internal energy will be equal to Q. And finally, we have the isothermal process. In the isothermal process, we have the system having thermally insulating walls except one boundary, which we have shown here. It is in contact with an energy reservoir that fixes its temperature. The energy reservoir is a system that has very large heat capacity. Alright, so in the isothermal process, the temperature is kept constant by forming one thermal contact with an energy reservoir. PV for an ideal gas is equal to nRT, so this is going to be a constant. And the PV curves will be called is a hyperbola, because it's P times V is a constant curve, and it's called each curve is called an isotherm because it corresponds to a constant temperature. So it's an isotherm. So if you plot pressure as a function of volume for an isothermal process, that's the hyperbola, and we see that we start with, let's say, this V initial, P initial, and we go to this V final, P final. We're going to have this curve called the isotherm, and the area underneath will give me information about the work done on the system. So how do I calculate the work done? It's minus from work integral from V initial to V final P dV. Now in this case, the pressure is related to volume. It is nRT over V dV. And nRT is a constant, so it comes out minus nRT integral from V initial to V final dV over V, and that integral gives me a natural logarithm, so minus nRT natural logarithm V final minus natural logarithm V initial, so this will be equal to minus nRT natural logarithm V final over V initial. And finally, when I operate the minus sign on the natural logarithm, I have natural logarithm of V initial over V final. So this will be the way to calculate the work done on the system with an isothermal process. And what is it saying? If V initial is less than V final, you're going to have negative work done, which means it is an expansion. We will see more examples of this in the next video for the applications of the first law of thermodynamics.